So next topic is thermal fatigue and its application in metal cutting. Thermal fatigue. Okay, so the last lectures I said the external force acting on a material, first it will be a tensile load, then it will be a compressive load, then it will be a tensile load. Such type of cyclic load is the reason for the fatigue. Okay, so here it is tensile, then it is compressive. Okay, so such type of cyclic load when it acts on a material or on a body leads to the fatigue failure. Okay, next we are discussing the thermal fatigue. So such type of cyclic load also develop or act on a body because of the thermal variation. Okay, so we already discussed the expansion or stress develop on a body because of thermal temperature variation. That is the thermal stress. Okay, what is the value of thermal stress? Thermal stress is equal to, what is the value? Sigma equal to E alpha delta T. E alpha delta T. Okay, so this is my body and I fix this end of this body. I change the temperature from T1 to T2. Is there any thermal stress in this body? Anyone? Is there any thermal stress in this body? Yes. I change the temperature from T1 to T2. That means there is a delta T. And this for this material there is an alpha value, and for this material there is a Young's modulus value. So E alpha delta T. Is there any thermal stress? No. Okay. One end is fixed. When one end is fixed, this end is free. This end is free. When I change the temperature, what happens? This will elongate or this will contract depending upon the alpha value. Okay, this end is free, so it can easily elongate with respect to the change in temperature. So there is no stress developed on this body when this end is free or both ends are free. But when this sigma value is developed, thermal stress is developed when both ends are fixed. When both ends of this component is fixed, then there is no provision for the expansion or contraction of this body when I change the temperature by an amount delta T. So in this case, there will be a thermal stress. Okay, that is the thermal stress variation. So I take a body. And this body is actually, for example, this is a component in a furnace. This is a component in a furnace. Okay. So when I heat the furnace, what happened? Its temperature is increased from a particular value to 80 degrees Celsius. Its temperature of this component is increased from to 80 degrees Celsius when I heat the furnace. And after some process, I cool the furnace. Then the temperature is reduced to 33 degrees for 30 degrees Celsius. Okay, so initially when I heat the furnace, its temperature increased to 80 degrees Celsius. Then after some process, I switch off the furnace. Then its heat reduced to or it cooled to 30 degrees Celsius. Again for another process, again I heat the furnace. By switch on the furnace, it is again heated to 80 degrees Celsius. After switch off, it is again reduced to 30 degrees Celsius. So next I am going to plot the variation of temperature. The variation of temperature. What happened? Initially there is a temperature of 30 degrees Celsius. It is increased to 80 degrees Celsius, then reduced to 30 degrees Celsius, then increased to 30, 80, then 30, 80, 30 with respect to time. So the temperature is varying with respect to time in a cyclic manner. Increase to peak value, decrease to minimum value, again increase, decrease. So this is cyclic variation. So the temperature change here is a cyclic change. Okay. So when the temperatures change in a cyclic manner, what happened to the stress value? What happened to the stress value of this stress develop? Thermal stress develop on this component. Both ends of this component is fixed. What happened? എന്താ പറ്റുന്നത്?
ടെമ്പറേച്ചറിന് വേരിയേഷൻ വരുന്നതനുസരിച്ച് തെർമൽ സ്ട്രെസ്സിന് വേരിയേഷൻസ് വരും.
Yes. So correspond here the temperature variation is in a cyclic manner. Corresponding to this cyclic manner temperature change, the thermal stress also will vary in a cyclic manner. In a cyclic manner. Okay, so the stress also vary with respect to temperature variation. Based on this formula, when the temperature is varied in a cyclic manner, the stress also will be varied in a cyclic manner. So this is the temperature variation, and this is the stress variation. So this type of temperature variation can see in different engineering application. For example, in case of engine, I take an engine. So this is my piston. Okay. During when I fuel and during the explosion or the power stroke, what happened? There will be explosion of the fuel. This surface, for example, this piston subjected to higher temperature. This piston subjected to very high temperature. Then during the exhaust stroke, the exhaust gases are removed during the exhaust stroke. This piston get cooled. So during the power stroke, it is heated. During the exhaust stroke, it is cooled. Again, the next cycle, again during the power stroke, the piston is heated. Again, it is cooled. So this will continue in a cyclic manner. The temperature change will continue in a cyclic manner. So the piston subjected to fatigue load, thermal fatigue load. Similarly, in most of the engineering application, these materials are subjected to thermal fatigue. Thermal fatigue. Okay, so thermal cycle or thermal fatigue is causes because of the expansion and contraction, which will act as tensile and compressive load. So during expansion, during this higher temperature, what happened? There will be an expansion of this component. Expansion of this component. In the lower temperature or during cooling, what happened? There will be a contraction of this component. So expansion, contraction, expansion, contraction. That is a fatigue load. Correspondingly, a tensile load and a compressive load will be developed. So again, due to temperature change, a fatigue load or fatigue stress will be developed. There will be a fatigue failure. Okay. So thermal fatigues. What are the applications of thermal fatigue in metal? Yes.
ആദ്യം ഒരു ബീമിന്റെ എക്സാമ്പിൾ പറഞ്ഞില്ലേ?
ഇതിന്റെ
ആദ്യം ഒരു ബീം വെച്ചിട്ട് എക്സാമ്പിൾ പറഞ്ഞില്ലേ? അവിടെ തെർമൽ സ്ട്രെസ് ആക്ട് ചെയ്യുന്നില്ല.
തെർമൽ സ്ട്രെസ് ഇല്ലാന്ന്.
അത് പക്ഷേ നമ്മളവിടെ ആ ഒരു ടെമ്പറേച്ചർ കൂടുതൽ കൊടുക്കുമ്പോ ആ ഒരു ബീമിന് ശരിക്കും ഒരു ഇലോങ്ങേഷൻ സംഭവിക്കുന്നുണ്ടല്ലോ.
അത് അവിടെ അത് ഞാൻ മെക്കാനിക്സ് സോളിഡ്സിൽ തെർമൽ സ്ട്രെസ് പറഞ്ഞപ്പോ പറഞ്ഞായിരുന്നു. അതായത് എന്താ പറയാ, നമ്മളിവിടെ ഫ്രീ എൻഡ് ആണ്, അല്ലെങ്കിൽ വെറുതെ ഇരിക്കുന്ന ഒരു സ്മൂത്ത് സർഫസിൽ ഇരിക്കുന്ന ഒരു ബോഡിയിൽ എത്ര ടെമ്പറേച്ചർ ചേഞ്ച് വന്നാലും സ്ട്രെസ് സീറോ ആയിരിക്കും. കാരണം അതിന് ഫ്രീ ആയിട്ട് എക്സ്പാൻഡ് കോൺട്രാക്റ്റും ചെയ്യാം. അതിന്റെ എക്സ്പാൻഷൻ കോൺട്രാക്ഷനും നമ്മൾ പ്രിവെന്റ് ചെയ്താൽ മാത്രമാണ് അവിടെ ഒരു സ്ട്രെസ് ഡെവലപ്പ് ചെയ്യുള്ളൂ. ഓക്കെ.
Thanks.
അപ്പൊ ഏത് ബോഡി ആണെങ്കിലും ഇപ്പൊ ഇവിടെ ആണെങ്കിൽ നോക്കിയേ ഈ പിസ്റ്റന്റെ ഫ്രീ എക്സ്പാൻഷൻ കോൺട്രാക്ഷൻ പ്രിവെന്റ് ചെയ്യായി കണക്ടിംഗ് റോഡും ഈ ഗ്യാസും എക്സ്പ്ലോറഡ് ഗ്യാസും. ഓക്കെ, so this piston is acting like a two ends fixed beam. It's like acting like a two end fixed beam. കാരണം രണ്ട് എൻഡിൽ നിന്നും അതിന്റെ എക്സ്പാൻഷൻ കോൺട്രാക്ഷൻ പ്രിവെന്റ് ചെയ്യാനുള്ള സപ്പോർട്ടിംഗ് കണ്ടീഷൻസ് ഉണ്ട്. Okay. So, what are the applications of this thermal fatigue on metal cutting? So, after machining, so see this gear. After machining, we can see burrs. See these burrs, some irregularities on the tooth of this gear. So, this burrs can be removed by this thermal fatigue. So, this is the one advantage. This is a application of thermal fatigue on a metal cutting process. Okay, so by means of a shock wave, so by the thermal shock, actually we can vaporize this burrs from the component. Thereby we got a smooth surface. So that is one of the applications of thermal fatigue. Okay, we can remove the burrs from the surface of the components by means of thermal shock. Okay, second application is in a metal cutting, this type of milling wheels. This is the milling cutter. Okay, so this milling cutter tooth affect fatigue load. How? For example, this is my workpiece. This is my workpiece. Okay, so when the milling cutter starts to rotate or remove the material from the workpiece, so this cutting point, this cutting tooth, when it is touched on the workpiece, there will be a heat generation on this tooth. Okay, during the machining process, when it cut the material from the workpiece, there will be a heat generation in this tooth. Okay, so the temperature is increased on this tooth. Then after cutting, what happened? This tooth is moved to this direction, move in this direction. So during this movement, the heat is dissipated from the tooth into the atmosphere. So that is a cooling process. So when we consider this tooth, during the cutting process, there will be heat generation on this tooth, and after cutting, up to the next cutting process, there will be a cooling process. Okay, the heat is dissipated from this tooth into the atmosphere. So this all tooth in this milling cutter subjected to this type of cyclic stress. Okay, there is a heat generation during the cutting process. A heat generation will be there, and after cutting, the heat is dissipated from the tooth of the milling cutter. So this will be a cooling process. Again, on the next cutting, a heat generation, and after cutting, a cooling process. So this will be a cyclic process. Okay, so the fatigue load will be developed on the tooth of the milling cutter. Similarly, all the tool subjected to this type of cyclic load. So this will reduce the tool life. Tool life will be reduced by this fatigue failure. Okay, and similarly another one, that the hot forged dies. See this hot forged dies. This one is a forging die, and this is the bottom forging die. Again, during the pressing process or hammering process, these dies are in contact with this molten material or very hot workpiece. During the hammering process or pressing process, these dies are in contact with the very hot workpiece material. Okay, and after this pressing process, what happened? These dies are in contact with the atmosphere air. Okay, so during this contact with the workpiece, there will be a heat generation. Okay, And after this pressing process, when it the dies when come contact with the atmospheric gas, there will be heat dissipation or cooling process. Again, this process is continued. So in this case of hot forging dies also, there will be a cyclic load. So that also leads to the fatigue failure of these dies. Okay. So, there are different such examples we can see from engineering applications where subjected to such type of fatigue load. So, in case of metal cutting and this hot forging process, these are the two examples of thermal fatigue. Okay. Any doubt? Any doubt in this? Milling cutter or any type of tool and forging dies. Okay. So effective temperature on fatigue life, as the temperature increases, the crack growth rate will increase. So the increase in temperature decrease the fatigue strength. So the temperature is an important, it's not a cyclic temperature. Even at a high temperature, the fatigue life will reduce, because when a crack is formed, the propagation of the crack is accelerated with respect to the temperature. Okay, so the crack propagation is accelerated by means of increasing the temperature. So to reduce the fatigue failure, we have to use material at a lower temperature. Okay, at a higher temperature, there's a more chance for fatigue failure, because the crack propagation will affect with the temperature. It's directly proportional. The crack propagation rate and the temperature is directly proportional. With respect to increase in temperature, there is a more chance for higher rate of crack propagation. Okay, so that is the effect of temperature on fatigue life. And another important, so we already covered the fatigue portions. Any doubt in this fatigue failure? And so it's a very important type of failure in engineering application, because most of our engineering components subjected to fatigue load, cyclic load. That cyclic load may be direct stress or maybe because of the thermal variation. Okay, so this fatigue failure we should consider while designing any component. We should consider the fatigue failure of the component. Okay, or what is the easiest method to remove such failure, fatigue failure? Anyone? എങ്ങനെ നമുക്ക് ഈ fatigue failure avoid ചെയ്യാം? Anyone? Easiest method to remove the fatigue failure of the components? Anyone?
ഷാർപ്പ് എഡ്ജുകൾ കൊടുക്കാതിരിക്കുക.
അത് കംപ്ലീറ്റ്ലി നമുക്ക് റിമൂവ് ചെയ്യാൻ പറ്റില്ല. For a ferrous material, for a ferrous material, what is the important method to avoid complete fatigue failure? ഷാർപ്പ് എഡ്ജ് ഇത് ഇങ്ങനെ കുറെ ഫാക്ടേഴ്സ് ഉണ്ട്. അല്ലാതെ എന്തൊരു കംപ്ലീറ്റ്ലി അവോയ്ഡ് ചെയ്യാൻ പറ്റിയ ഒരു മെത്തേഡ് എന്താണ്?
യൂസ് ഓഫ് ആൻ അലോയ്.
അലോയ് ചെയ്താലും അതിലുണ്ടാവും, ഉണ്ടാവും.
endurance limit വെച്ച് ഡിസൈൻ ചെയ്താൽ മതി.
Exactly. Endurance limit. That is very important, this endurance limit. If we design with respect to endurance limit, there is no such fatigue failure. Even at a very high stress concentration, even at very high temperature, there will not be any fatigue failure if we design with respect to the endurance limit. We have to design at a stress which is lower than the endurance limit or fatigue limit. Then there is no problem with the fatigue failure. Okay, so when we design any component, നിങ്ങൾ S8 പഠിക്കുക, അല്ലെ S7 ഡിസൈൻ ഓഫ് മെഷീൻ എലമെന്റ്സ് എന്ന് പറഞ്ഞ സബ്ജക്ട് ഉണ്ട്. അപ്പൊ അവിടെ നിങ്ങൾ ഡിസൈൻ ചെയ്യുമ്പോൾ, if you design a component which is subject to such type of thermal fatigue load or such type of any cyclic load, you have to design based on the endurance limit. not based on the yield stress, not based on the ultimate stress, not based on the failure stress. The design should be based on the endurance limit. Okay, of course, this endurance stress will be less than yield stress and ultimate stress. Okay, but if you design the components based on the endurance limit, we got complete prevention from, or we can avoid completely this type of fatigue failure. Okay, so this is the very important factor while designing any component. This is only applicable for ferrous material, not applicable for any other non-ferrous material. Okay, for non-ferrous material, the SN curve is not like this, not a straight line after a particular point. So we cannot see any such type of endurance limit in the non-ferrous material. But for ferrous material, we can use this method to avoid such type of fatigue failure. Okay. And another topic is fracture toughness. Okay, we already discussed the toughness. Toughness is the energy required for. So toughness, that is the from the stress strain graph, we can calculate the toughness of the material. That is the area under the stress strain graph. This is the energy required for fracture of the material. Okay, by ISO test or Charpy impact test, we can calculate the energy required for the fracture of the material. That is the toughness of the material. But there is another toughness that is called fracture toughness. Fracture toughness. What is a fracture toughness? What is the difference between ordinary toughness and fracture toughness? In case of fracture toughness, it is the ability of the material with the indigenous cracks to resist the fracture by absorbing energy. Okay, also defines the resistance to crack propagation. That is a fracture toughness. So in case of toughness is nothing but it is the amount of energy required to fracture this component completely. Initially, this component, we assume this component is without any such type of cracks initially. So for the crack initiation and crack propagation, how much amount of energy is required? That is toughness. Okay, but fracture toughness, initially there is a crack in a material. Initially there is a crack in this material. And then how much amount of energy is required for the initiation, propagation of this crack? Some amount of energy is required for the propagation of this crack. That energy is called fracture toughness. Okay, so that is the difference between toughness and the fracture toughness. When we calculate the toughness, there is no such type of cracks. So amount of energy required for the initiation of crack and the propagation of crack is called toughness. But here in this material, initially there is a crack, and how much amount of energy is required for the propagation of crack? That is the fracture toughness. Okay, so the fracture toughness is the ability of the materials to resist the fracture, or fracture toughness is quantitative way of expressing material resistance to brittle fracture. And the fracture toughness is the one of the most important property of the material for many design application. So for designing application, we mainly use this fracture toughness because most of our material will have some amount of cracks. There will be some amount of cracks. So we have, so already there is a crack. So how much amount of required energy for the crack propagation? That is fracture toughness. So we have to design based on the fracture toughness for withstanding the material without any crack propagation. Okay, so fracture toughness values can be practically applied for many areas for the material selections to avoid any catastrophic failure. Okay, for example, in case of a nuclear power plant, or in case of aeronautics, offshore applications like a ship, etc., we can use the fracture toughness for the design. Okay, for the bridges or for pipelines, everywhere for the design, instead of using toughness, we can use fracture toughness. And another advantage is that rehabilitation of the old bridges or pressure vessel, we use fracture toughness for the design calculation. Okay, that is about fracture toughness. So we complete the one area of failure, that is important area of failure, that is fatigue failure. Next important failure is creep. Another. So fatigue failure is because of cyclic load. Next mode of failure is creep failure. And before studying creep failure, I have 3 questions. Where do tungsten filament bulbs fuse? നിങ്ങൾ നേരത്തെ നിങ്ങളുടെ വീട്ടിൽ tungsten filament bulbs യൂസ് ചെയ്തത് അല്ലേ? So tungsten filament bulbs are fused after some time. What is the reason for that? There is a life for the tungsten filament bulbs, and main reason for the failure of this bulb is tungsten filament fuse. What is the reason for the filament fusing? Anyone? Anyone? What is the reason for the tungsten filament fuse failure?
അതിന്റെ അകത്തുണ്ടാവുന്ന ഹീറ്റ് കാരണം.
No, it's not because of the heat generated. Because tungsten, I think the melting point of tungsten is around 3,400 degrees Celsius. Okay, it's very high melting point for the tungsten. Okay, actually this much amount of heat is not generated inside the bulb. If this much amount of heat is generated, the entire thing, the glass or the this junction, everything will melt it. So this much amount of heat will not generated inside the bulb. So there is no melting of this tungsten filament. So that is not the reason. The reason is this creep. Creep failure is the reason for the failure of the tungsten filament. And next question, how do the glaciers moves? In the Himalayas, we can see the glacier movements. What is the reason for the glacier movement? The answer is creep. Creep failure is the reason for the glacier movement. And third question, what limits the life of a jet engine turbine blades? There is a life for the turbine blades, that jet engine. Okay, and that also, in this also, the reason is creep failure. So we will discuss about the creep failure. In this lecture, I am just giving the introduction about the creep failure. So this is an experiment I am doing to investigate the creep failure. So here I am using 2 spring. Okay, and this spring 1 is made with the aluminum. This spring 1 is made with the aluminum. Okay, and this spring 2 is made with the alloy of lead and tin. Okay, lead tin alloy. That is the soldering iron material. Spring 2. So at the time 0 minute, both has same length. Spring 1 and spring 2 has same weight. There is no external weight acting on this 2 spring. Only self weight is acting, and this 2 spring is hang on this wall. Okay, this 2 spring 1 and spring 1 made with aluminum, spring 2 made with a lead tin alloy is hang on this wall. At the time 0, T0, both has same length. Okay, and then when I conduct the experiment at a different time, I measure the variation of the length of both spring. I saw that for the spring 1, there is no change in the length after 5 minutes. After 5 minutes, there is no change in length. Even at a 0 time, this is the length, and after 5 minutes, that length is not changed. Okay, but for spring 2, which is made with the lead and tin alloy, after 1 minute, we can see at T0, this is the length. At T1, this is the length. At T5, this is the length. The length is increased with respect to time. Actually, there is no external load acting on this. There is no such external load acting on these 2 springs. Even at a spring 1 and a spring 2, I am not adding any external load. Only self weight is acting on this 2 spring. But spring 1 there is no elongation after time, but here for spring 2, with respect to the increase in time, there is an elongation. We can see an elongation on the spring 2. And what is the reason for this elongation of the spring 2 only? There is no elongation for spring 1. But for spring 2, with respect to increase in time, okay, at a constant load, there is no change in the load acting on spring 1 and 2. Okay, with respect to increase, there is only one factor here. What is that? Time. Okay, here the time is only varying. Time is varying from 0 to 5. There is no change in the load. There is no change in the atmospheric condition. Okay, with respect to change in time, there is a deformation in the spring 2. And this deformation is because of the creep. Okay, this deformation of the spring 2 is because of the creep. So next I'm going to define creep failure. Creep is the time dependent, continued plastic deformation at a constant load or stress at a high temperature. At a high temperature. What is the creep? Creep failure is failure is the time dependent. Here we can see it is a time dependent variation. The elongation is dependent only on time. With respect to time, the elongation is happened. So it is a time dependent. It's a continued plastic deformation. It is not a sudden variation. At t equal to 0, this is the elongation. At t equal to 1, this is 1. At t equal to 5, this is the elongation. So it is a continued plastic deformation. It is not a sudden plastic deformation on the spring. With respect to time, slowly the plastic deformation happens slowly with respect to time increase. Okay, so continued plastic deformation at a constant load. There is no change in the load. I'm not adding any weight on this 2 spring. There is only self weight is acting on this 2 spring. But here the with respect by adding based on this self weight, there is no change in the deformation or length. But here under the self weight, there is a deformation for this spring 2. So at a constant load or stress at a high temperature. Here the temperature, even here we conduct the experiment at a room temperature, but there is a temperature change in this 2 material. Okay, but here, the experiment is actually conducted at a room temperature. Okay, 30 degrees Celsius. But for this 2 material, there is a temperature change. I will explain what is that. Okay, so there are 2 factors which are affecting this elongation of this spring 2. What are they? First one is the time. The time dependent variation. Second one is the temperature. And there is here in this experiment, the load is constant. Such type of deformation or such type of failure is called creep failure. Okay, creep failure. And the temperature we provide is greater than 0.5 Tm. So what happened to this 2 material? This aluminum material is not, there is no elongation we can see in this aluminum material, but there is elongation for this tin lead alloy. What is the reason for that? The reason is the effect of temperature. Effect of temperature. Creep is a high temperature phenomena. Okay, this phenomena is a high temperature phenomena. Creep. Okay, so let us check the 2 material. The spring 1 is made with aluminum. Spring 2 is made with a tin lead alloy. Okay, so what is the melting point of aluminum? Melting point of aluminum is 660 degrees Celsius. But for tin lead, it is only 183 degrees Celsius. We already discussed the tin lead phase diagram. In the phase diagram, in the eutectic point, the melting point is 183 degrees Celsius. That is why this is a very low temperature, melting temperature. That is why we use this tin lead alloy for soldering. Okay, at a very low temperature, we can melt the tin lead alloy. That is why we use this tin lead alloy for soldering application. So it has very low temperature, melting temperature. But it has, this aluminum has 660 degree melting temperature. Okay. I am converting this into room temperature, Kelvin. I am converting this degree Celsius into Kelvin scale. So Add this with 273. So 660 plus 273, 933, 183 plus 273, 456. Okay. Next, I am taking the ratio of room temperature in Kelvin with respect to melting temperature in Kelvin. What is the room temperature? For example, our room temperature we can take as 30 degrees Celsius. So in Kelvin scale, it is equal to 30 plus 273, 300. Okay. So room temperature in Kelvin is equal to, so I am doing this experiment at a room temperature of 30 degrees Celsius. So both the material will be at a 30 degrees Celsius. Okay. So room temperature is 300 Kelvin, 30 degrees Celsius equal to 300 Kelvin. So I am taking the ratio 300 divided by the melting point in Kelvin for aluminum. That 300 by 933, that is equal to 0.32. Okay. And for this tin lead alloy, room temperature is 300 divided by the melting point in Kelvin, that is equal to 456, that is equal to 0.66. So we got two ratio, 0.32 for aluminum. Even at a room temperature, this ratio is 0.32 for aluminum. For tin lead alloy, it is 0.66. We can see this is almost double. For tin lead alloy, this ratio is almost double than that of aluminum. And this ratio is the reason for this elongation of this tin lead alloy. With respect to time, this elongation is because of this ratio, higher ratio, 0.66. Or we can say, here in this creep phenomena will significant when this ratio is greater than 0.5. Okay, if this temperature at which this phenomena occur is if it is greater than 0.5 times of this melting point, 0.5 times of its melting point. Here it is 0.66. That means it is greater than 0.5. So that is why lead tin spring subjected to creep failure or elongation, because here it is greater than 0.5 times of the melting point for this lead tin material. But for aluminum, it is less than 0.5 times of the melting point. So it will not subject to any type of creep phenomena. But here it is greater than 0.5 times of melting point. So creep will be significant only when the temperature where components is greater than 0.5 times of the T melting point. Okay, so that is the reason for this type of elongation on the tin lead material. Any doubt? Any doubt in this? So even the temperature is here, it is 30 degree. Here the temperature, both the material temperature is 30 degree room temperature. But when we take the melting point, it is 0.55, it is 0.5 times of the greater than 0.5 times of the melting point. Okay, for this material. But here for aluminum, it is less than, the room temperature is less than 0.5 times of melting point. It is less than 0.5 times of melting point for aluminum, but it is greater than 0.5 times of room temperature. Okay, so if it is greater than 0.5 times of room temperature, then there will be a creep phenomena. So we can see a creep phenomena here. This is not visible in this here. Any doubt? Any doubt in this about this experiment? Any doubt? Anyone? മനസ്സിലായോ അത്? എക്സ്പെരിമെന്റ് ചെയ്ത് മനസ്സിലായോ? അപ്പൊ ക്രീപ്പ് ഈസ് എ ഹൈ ടെമ്പറേച്ചർ ഫിനോമിന. ഹൈ ടെമ്പറേച്ചറിൽ നടക്കുള്ളൂ. ഇറ്റ് ഈസ് എ ടൈം ഡിപെൻഡന്റ് ഫിനോമിന. ഇറ്റ് ഈസ് എ കോൺസ്റ്റന്റ് ലോഡ് ഫിനോമിന. മൂന്ന് കാര്യമുണ്ട്. കോൺസ്റ്റന്റ് ലോഡിലാണ് സംഭവിക്കുന്ന ക്രീപ്പ്. നമ്മൾ ഒരിക്കലും ലോഡ് ഇൻക്രീസ് ചെയ്യോ ഡിക്രീസ് ചെയ്യോ വേണ്ട. ഒരു മെറ്റീരിയൽ ആക്ട് ചെയ്യുന്ന കോൺസ്റ്റന്റ് ലോഡായിരിക്കും ആക്ട് ചെയ്യുന്നത്. വി ആർ നോട്ട് ഇൻക്രീസിങ് ഓർ ഡിക്രീസിങ് ദ ലോഡ്. Vertically, we increase and decrease fluctuating load. But here it is a constant load. So it is a constant load phenomena. It is a high temperature phenomena. High temperature phenomena. It is a time dependent phenomena. These are the three important characteristics of a creep failure: constant load, high temperature, time dependent phenomena. Any doubt?
അപ്പൊ ഈ ടെമ്പറേച്ചറിന് ഇതില്ലാന്നുണ്ടെങ്കിൽ ക്രീപ്പ് സംഭവിക്കില്ല. ടെമ്പറേച്ചർ ഡിപെൻഡന്റ് ആണ്.
Yes, yes. 0.5 ഒരു മെറ്റീരിയൽ എടുത്തു. ആ മെറ്റീരിയലിന്റെ മെൽറ്റിംഗ് പോയിന്റ് ഫോർ എക്സാമ്പിൾ TM ആണെന്ന് വെച്ചോ. ഒന്ന് മൈക്ക് ഓഫ് ചെയ്തേ. ഓക്കെ, ഒരു മെറ്റീരിയൽ എടുത്തു. ആ മെറ്റീരിയലിന്റെ മെൽറ്റിംഗ് പോയിന്റ് ഈസ് TM. ഓക്കെ, ആൻഡ് അത് അപ്ലൈ ചെയ്യുന്ന, അത് യൂസ് ചെയ്യുന്ന അറ്റ്മോസ്ഫിയറിന്റെ ടെമ്പറേച്ചർ, അവിടുത്തെ റൂം ടെമ്പറേച്ചർ ഇഫ് ഇറ്റ് ഈസ് ഗ്രേറ്റർ ദാൻ 0.5 ടൈംസ് ഓഫ് TM, then ക്രീപ്പ് ഉണ്ടാവും, ക്രീപ്പ് ഫിനോമിന ഉണ്ടാവും. ഓക്കെ, ഈ മെറ്റീരിയലിന്റെ മെൽറ്റിംഗ് പോയിന്റ് ഈസ് TM മെൽറ്റിംഗ് പോയിന്റ് ടെമ്പറേച്ചർ ആണ്. TMന്റെ 0.5, ഹാഫ് ഓഫ് ദി TMനേക്കാൾ ഗ്രേറ്റർ ആണ് അവിടുത്തെ റൂം ടെമ്പറേച്ചർ എങ്കിൽ then there will be a creep phenomena. Hello?
ഈ റൂം ടെമ്പറേച്ചർ കോൺസ്റ്റന്റ് ആണോ ലോഡ് പോലെ?
റൂം ടെമ്പറേച്ചർ കോൺസ്റ്റന്റ് ആ. ഇപ്പൊ ഈ എക്സ്പ്ലോർ ചെയ്തപ്പോ ഇവിടെ 30 ഡിഗ്രി സെൽഷ്യസ് എടുത്ത്.
ഓക്കെ
ഓക്കെ
സാർ, ഇപ്പൊ നമ്മളൊരു ബോഡിയിലേക്ക് കോൺസ്റ്റന്റ് ലോഡ് കുറച്ചധികം സമയത്തേക്ക് കൊടുത്തോണ്ടിരിക്കുകയാണ്. ഒരു എക്സാമ്പിൾ പറയുകയാണെങ്കിൽ നമ്മുടെ ഈ ഡെസ്ക് ഇല്ലേ, നമ്മളെ ക്ലാസ് റൂമിലൊക്കെ ഇടുന്ന ഡെസ്ക്, അതിന്റെ നമ്മൾ കാല് വയ്ക്കുന്ന പടിയില്ലേ, അതിപ്പോ നമ്മൾ അതില് കണ്ടിന്യൂസ് ആയിട്ട് ലോഡ് കൊടുക്കുന്ന ഒരു സാധനമാണ്. അതില് നമ്മള് ഇപ്പൊ ഒരുപാട് സമയത്തേക്ക് നമ്മൾ ലോഡ് കൊടുക്കാന്ന് വിചാരിക്കുക. അത് നോർമലി അതിന് ഡീഫോർമേഷൻ സംഭവിക്കുന്നുണ്ട്, അത് വളച്ചു പോകുന്നുണ്ടല്ലോ. അത് ശരിക്കും ഒരു ക്രീപ്പ് അല്ലേ?
അതൊരു ക്രീപ്പ് ആവണമെങ്കിൽ, അതൊരു ക്രീപ്പ് ഫെയിലിയർ ആവണമെങ്കിൽ അവിടുത്തെ ടെമ്പറേച്ചർ അതിന്റെ മെൽറ്റിംഗ് പോയിന്റിന്റെ ഹാഫ് ആയിരിക്കണം. ഓക്കെ, അവിടുത്തെ ആ ഡെസ്ക് ഇരിക്കുന്ന അവിടുത്തെ ടെമ്പറേച്ചർ ആ വുഡിന്റെ മെൽറ്റിംഗ് ടെമ്പറേച്ചർ ഉണ്ടാവും, അതിന്റെ ഹാഫിനേക്കാൾ ഗ്രേറ്റർ ആണെങ്കിൽ അത് ക്രീപ്പ് കൊണ്ടായിരിക്കും. ഓക്കെ, അപ്പൊ എല്ലാ കേസും നമുക്ക് ഈ പറഞ്ഞ എന്തെങ്കിലും ഡിഫ്ലക്ഷനോ ഡിഫോർമേഷനോ ഉണ്ടാവുമ്പോ അത് ക്രീപ്പ് കൊണ്ടാണെന്ന് പറയാൻ പറ്റില്ല. ക്രീപ്പ് മെയിൻലി ഒബ്സർവ് ചെയ്യുന്നത് എന്ന് പറഞ്ഞാൽ ഹൈ ടെമ്പറേച്ചർ ആപ്ലിക്കേഷനാണ്. ഇപ്പൊ ഫോർ എക്സാമ്പിൾ നമ്മൾ ജെറ്റ് എഞ്ചിന്റെ കേസ് പറഞ്ഞില്ലേ, ജെറ്റ് എഞ്ചിൻ എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ അവിടെ ഹൈ ടെമ്പറേച്ചർ ആണ് എപ്പോഴും. അപ്പോൾ ഇവിടുത്തെ മെറ്റീരിയലിനേക്കാൾ അതിന്റെ ടെമ്പറേച്ചറിന്റെ 0.5 ടൈംസിനേക്കാൾ ഗ്രേറ്റർ ആണ് അവിടുത്തെ ടെമ്പറേച്ചർ വരുന്നുണ്ടെങ്കിൽ there is a chance for creep failure. Okay, ഇനി about this tungsten filamentന്റെ വെരി ഹൈ മെൽറ്റിംഗ് പോയിന്റ് ആണ്. പക്ഷെ ആ മെൽറ്റിംഗ് പോയിന്റിന്റെ 0.5 ടൈംസിനേക്കാൾ ഗ്രേറ്റർ ആണ് ആ ഫിലമെന്റ് ഇരിക്കുന്ന ടെമ്പറേച്ചർ എങ്കിൽ ആഫ്റ്റർ എ ലോങ് ടൈം, ഒരു കുറച്ച് ടൈം കഴിഞ്ഞാൽ, ഇറ്റ്സ് എ ടൈം ഡിപെൻഡന്റ് ഫിനോമിന. ഓക്കെ, ആഫ്റ്റർ എ ടൈം ഇത് ഫെയിൽ ആവോ, ദാറ്റ് ഈസ് എ ക്രീപ്പ് ഫെയിലിയർ. അതുകൊണ്ടാണ് ടങ്സ്റ്റൺ ഫിലമെന്റ് ഒന്നും ബൾബൊന്നും പെട്ടെന്ന് ഫെയിൽ ആവില്ല. കുറച്ച് ഒരു വർഷമോ അല്ലെങ്കിൽ കുറെ നാൾ കഴിഞ്ഞിട്ടാ ഫെയിൽ ആവുള്ളൂ. അപ്പൊ അത് ടൈം ഡിപെൻഡന്റ് ആയിട്ട് ഇങ്ങനെ പതുക്കെ ഡീഫോർമേഷൻ സംഭവിച്ച്. ഓക്കെ, അപ്പൊ അതിനായിട്ടുള്ള അറ്റ്മോസ്ഫിയർ അവിടെ ഉണ്ട്. ഏതാ, ആ ടങ്സ്റ്റൺ ഫിലമെന്റിന്റെ മെൽറ്റിംഗ് പോയിന്റിന്റെ 0.5 ഹാഫിനേക്കാൾ ഗ്രേറ്റർ ആണ് ആ ഫിലമെന്റ് ഇരിക്കുന്നവിടുത്തെ ടെമ്പറേച്ചർ. ഓക്കെ, അപ്പൊ അങ്ങനത്തെ ആ ഒരു ടെമ്പറേച്ചറിൽ കുറെ നാൾ ഇരിക്കുകയാണ്. അപ്പൊ ഇതുപോലെ ഡിഫോർമേഷൻ ഉണ്ടാവും, പതുക്കെ ഇതുപോലെ ഡിഫോർമേഷൻ ഉണ്ടായി സഡൻലി ഫെയിൽ ആവും. ഇതുപോലെ ഡിഫോർമേഷൻ ഉണ്ടായി സഡൻലി ഫെയിൽ ആവും. അങ്ങനെയാണ് ക്രീപ്പ് ഉണ്ടാവുക. But temperature is an important factor, time is an important factor, load also factor, but load is not varying. Load is a constant load. Okay, ഇത്ര ഞാൻ എടുക്കുന്നുള്ളൂ. ഇപ്പൊ ക്രീപ്പ്, ഫെറ്റിക്, ഇത് രണ്ട് ഇമ്പോർട്ടന്റ് ആയിട്ടുള്ള. ഇനി നിങ്ങൾ എന്താ എഗെയിൻ നിങ്ങളുടെ എസ്7 എസ്8 നിങ്ങൾ design of machine elements